Hey, I'm Nader from NVIDIA.
I'm Carter from NVIDIA.
Hey, and I'm Kyle from NVIDIA.
Today on episode 2 of The Stack, we're talking about NVIDIA Dynamo with none other than Kyle, who is the Dynamo architect.
One of the Dynamo architects.
One of the Dynamo
yes.
architects.
Well, thanks for having me on. Dynamo is actually out in the world, and I can finally say that. That feels really, really, really good.
Yeah, it's been super exciting to see and hear of you guys working on this.
Yeah, for months at this point. It was like sometime very early last year we started working on it. It feels good to get it out in the world.
Yeah. You know, it's funny. The first time we met, which was like right when we joined the company, we actually sat down and chatted about inference optimizations and so on. Maybe from like a high level, what is Dynamo?
Oh, that's a good question. Dynamo is a distributed inference framework for, in my mind, eking out or gaining significant performance from the size of deployment you're working on. Now, basically, when you're talking about deployment, if you have more users, right, you're going to need more GPUs to serve them the tokens that, basically are your product or help, are part of your product. And in the case of Dynamo, right, if you are trying to host this service and you get more users, well, you're just going to add on more and more GPUs, right? And the purpose of Dynamo, at least from my perspective, is to ensure that you have the correct levers in order to be able to basically optimize for the amount of GPUs you're running on, like more efficiently use the fact that you're using hundreds and hundreds of GPUs and using them, efficiently to serve tokens.
I think something interesting, like if we zoom out, what you can do on a GPU, you can fine tune, train, build new models, and then you could use them, which is what we call inference. When you're doing inference, would you say that like you could end up using way more compute because you could have way more users? Like that's the model actually running in production?
Yeah. I'm going to give a long answer to this because I think it's worth the time. Inference is a really interesting space because there are sort of like three things that determine whether or not you can use a model with a given application. Those three things are really the quality of the model, whether or not it's capable of completing the task that's been asked of it. And you see this with a lot of reasoning models. Like reasoning models are used to improve the quality of the output. And then
I think size is important there too, though, because when a lot of people hear like quality of model, they might just be like, okay, what makes this one better versus that one? But additionally, if you have 8 billion versus 70 billion versus 405 billion, that might also determine like, is that model capable of doing what you need it to?
Yeah, actually, that brings us into the next point, which is that basically one of the other axes is cost, right? If you have a big models traditionally, or in a lot of cases, require more compute to serve and more GPUs to serve, and therefore are more costly per token generated, right? And then the third axis is latency, right? If you have an application that requires things to be snappy, like if you're talking about like a chatbot that you're interacting with, if you want it to respond in a good amount of time, you also have to care about the latency of the application. And these three levers are kind of the core of what inference looks like for LLMs these days. It's finding the right system in addition to the right model that serves your application. I like to think of it a couple ways, and I can go into how Dynamo actually affects these levers in a sec. But let's think about like reasoning models for a sec, right? Really, what you do when you're doing reasoning, which is generating like tokens that are not produced in the final output. They're actually surrounded by a special thinking tag that you can just strip out and not use, is you're trading the latency, because you're generating more tokens, of your of this specific system in order to get better quality. You're also trading cost because you're generating more tokens.
And this is like when I'm using R1 and it's taking a long time and it's telling me that it's taking a long time and it's thinking through it. So you're saying like, yeah, we're getting much better quality, but at the cost of how much longer it takes me to get my output.
Yeah.
At the cost of, I'm running more cycles on the GPU.
Exactly, right? If you're doing, if you're like calling R1 and it's taking a while, it's probably generating a bunch of tokens in the background, right? And because of that, you are just going to take longer to produce an answer. And you're also going to generate more tokens, which obviously costs time on the GPU, which translates to watts or dollars. And, you are incurring greater cost. So there are actually like a lot of other ways that you can modify these axes, right? There are ways that you can trade cost and latency, for example. A common example of this would be speculation, which is basically using a smaller model to predict what a larger model would say, and then using the larger model to verify whether or not those tokens should be accepted or which set of tokens should be accepted. And in that case, right, what you're trading is you're actually generating more tokens, similar kind of in a way to reasoning, right? You're generating more tokens, but you're actually using those tokens to go faster instead of using those tokens to, produce a better quality output.
That's really, I haven't even heard of that. That's really interesting. Is that like, in my head, I think of it, if you're like an analyst who's producing something that maybe an executive will eventually approve, as if it's like their own stuff.
Yeah.
It's kind of like, well, it's cheaper for the junior employee to work on that, but the executive still has to be like, that's actually quality. I'll stamp my name
it's
on
like
that.
any creative process, right? You just kind of throw a bunch of stuff at the wall and then just kind of like carve in what you really want.
Yeah. Exactly. Right. And that's just like one of a plethora of techniques that exist in the realm of manipulating inference to meet your application.
Yeah.
What I wanted to finish this with, and because to return to your original question, is you sort of asked like, how is inference growing now that these models are getting better at reasoning and bigger and sometimes even smaller in some cases? We're getting smaller models that are more capable. Like the 70B of today is like a comparably accurate to like the 405 or trillion B or trillion, not a trillion B, a trillion, 3 years ago, right? We're better learning how to train our models. What this means is actually because we're improving on every single one of these axes, you can think of the space of applications as being gated by like some particular set of constraints, right? It has to be this fast, it has to cost this much, and it has to produce this good of an output, right? And as quality increases, as cost decreases, and as latency improves, you unlock more and more applications. So it's kind of like, you have a larger and larger area to reap tasks from, and the demand for inference grows more and more.
You know what's funny? I don't know if this is true, but like my running theory of like why 2024 was so good for code gen use cases is that you're relatively safe from some of the latency issues and the quality issues, because if it spits out bad code, I'm there to tell it, make this better. I'll sit through the latency because it's faster than me writing syntax.
I mean,
there's so many real world use cases where that's just unlocked.
Yeah, I think that's a really good example where like the specific attributes of the models at the time lent themselves to code generation, right? Like another good example of this would be like maybe an example that we don't have yet is if you have like a LLM that is capable of providing like personalized care for some like sort of illness, right? Like they're reading your genetic code and developing like some synthetic compound that can be fabricated in a lab and cures you of something. That is so incredibly valuable that the latency and cost of doing that are so high that it seems like, you should 100% do it all the time, right? Yeah. Like, and that's sort of like how this trade-off works, right? There are these sort of breakpoints where either like it gets so cheap or the quality gets so good or it gets so fast that like it unlocks a new application, right? And the speed at which we're unlocking new applications and like growing this three-dimensional space, because remember, it's like three axes, right? You're like kind of growing this three-dimensional space is just accelerating because there's more ways that we can trade off axes, and then there's more there's just better models.
You said Dynamo is distributed inference, and like that I have a lot of questions about, which I'm really excited to dive in on. When it comes back to those three axes, so like with R1, I am getting better quality, but the latency is higher. So is Dynamo something that gets us essentially like better latency on using reasoning models like DeepSeek R1?
Yeah, so that's a great question. Well, first of all, the answer is yes. But it's actually a little bit more complex because you have let's just focus on two axes at once right now. Let's assume the model is fixed. You have these two axes of latency and cost, right? I'm going to use the term by which they're described, which is the total throughput of the system and the TPS or tokens per second on the user side, right? Now, Dynamo allows you to use techniques like disaggregation, improved KV cache routing, global KV cache management, which we'll go into in a little bit, to essentially make it so that previously a latency target that you wanted to hit, you are able to serve many, many more tokens in aggregate basically decreasing the cost at that point, ISO latency or like.
Can you explain that again?
Yeah. So let's say that you have a given SLA and you have an existing system that's not running with Dynamo, right? And not running with the techniques that Dynamo leverages. It's fixed at some latency, right? And you have a certain amount of GPUs that are used to serve at that latency. Dynamo basically provides a multiplier on the
Token generation for that latency.
on the tokens generated total on that machine for that latency, which basically is Jensen shows in his keynote, or showed in his keynote, this curve, which is called like a Pareto frontier, which is the set of potential latency, the set of total user TPS, which is basically the user latency, versus total TPS, which is the cost metrics, right? And it kind of looks like this, right? It looks like this arc that goes from a lot of tokens generated, but very slow for each user, versus barely any tokens are generated, but the tokens that they generate for one user is fast, right? And you can sort of make that trade-off. You can choose a point on that Pareto frontier, and that's it. Basically, what Dynamo does is you can think of it two ways, which is either that it like doubles the y-axis or like pushes the x-axis out.
So I have a way of thinking about it, because I think as far as like where NVIDIA Dynamo sits, is it kind of how I think of it is almost like the logistics, like the supply chain, but for inference. And so, if you think of model optimizations, like you saw in R1, that's like if you made, a machine at a factory actually, more efficient or something like that.
Yeah.
But what Dynamo does is actually making sure that the overall logistics supply chain of getting the package to the end user much more efficiently is much faster.
Yeah, exactly. It's like machines in the factory versus the factory itself.
Yes.
Right? So Dynamo is like the thing that is the factory that's trying to improve itself to produce more. And the model itself, or the way the model is represented by the people that created it, is the machine.
Yeah.
Right. So that's a great way to think about it. If you have a bunch of machines in a factory, how do you get those machines to function the best way in order to produce the most output, right? Which is great for a bunch of reasons. It's economically good, better for the environment, right? Because we're per token, the watt cost is less, and it's just generally like improving efficiency.
So what were the three optimizations you just mentioned that Dynamo's
doing? So one, to be clear, that's not the only three, but the really three big ones that launched on Tuesday are sort of this disaggregation, which is basically taking two phases of LLM generation and splitting them apart for efficiency. And why don't we go into that, because I don't want to stop on this thread. Disaggregation is basically an improved pipelining technique for LLMs. So when an LLM is generating tokens, there's the input and then there's the output, right? So when you read in the input, one of the things that you need to do is you need to produce these KV values for attention, right? If anyone's heard of QKV attention, that's what we're talking about. We're talking about the K and the V. And we need to produce these KV values for attention because they're used to calculate basically the attention for future tokens. And in traditional, let's call it aggregated LLM inference, you end up with a situation in which the prefill, which is the generation of that KV, and the use of that KV to generate future tokens is basically it's co-located. It's on the same set of GPUs. And that has a couple of pitfalls. The first pitfall is that you have thrash, right? If you're constantly trying to do scheduling for each phase, it's kind of hard to say like, hey, I have like a prefill chunk of this size and I need to generate a token that depends on a bunch of other tokens that we've already calculated prefill for. How do I schedule them against each other? You end up with like a lot of like moderately non-optimal scheduling decisions.
Is this scheduling what you're putting into the KV cache versus using that to generate tokens?
It's scheduling what gets processed, because it's basically scheduling whether or not you generate KV tokens or use other KV tokens to generate other output tokens.
Would it be worth also diving in on like essentially the KV cache and prefill?
That's a great point. So the KV cache, as I said, right, it's these values that are used for attention. When attention happens, you combine them with a queue, a query, for the current token. And then you use that query and the K and V values to calculate the attention, which is basically how much should this new token or the next token that we're generating care about each of the values in attention.
Yeah. I think that like this is the breakthrough that we saw with transformers was that the original paper, attention is all you need, and my understanding is that the key and value matrices essentially will take in the input and kind of, for lack of a better term, weight each word in comparison to every other word in the sequence to sort of understand the reasoning of how they all fit together.
Yeah, the relationship between Q and K is how you get the weights, and then you use the V's or the values in order to actually you combine the V's based on that weighting to produce a result.
And so this is everything from the prompt to the generated tokens.
Everything. So it's the initial prompt. It's anything that's considered a part of the input, and then any token you generate after that gets re-added back into the cache. And becomes a part of the context as you're generating future tokens. Because you don't want to have gaps, right? You don't want to have the input and then generate a bunch and then have a gap of what you've generated because you're just going to lose your context. So you have this KV cache. So as you're generating, you're adding on new K and V values for the tokens that you've basically generated, and then you need to keep that KV cache unless you're using window detention, which we're not going to talk about. You need to keep that KV cache until the end of the query or after you answer, because if you throw it out, you'll have to recalculate it, right? Because it's needed for attention itself.
So it was funny. I hadn't heard this before, but you said traditional inference is, you called it aggregated inference.
Yeah.
So how do you separate the tokens generated from the KV cache if we just said that the KV cache is what's used to generate the future tokens?
Yeah, that's a great question. So basically,
I'm 5.
Well, no. Essentially, you're generating the tokens, or you're generating the KV for the tokens on the prefill machine. And the prefill machine actually does something really smart. It starts sending the K and V values incrementally as they're calculated each layer.
And you said prefill machine, meaning for Dynamo, we have a separate whichever GPU is doing the prefill.
So in disaggregation, when you split it apart, the machines that handle creating the K and V values are called prefill, and the machines that are responsible for taking that KV and generating new tokens with it and generating new KV for those tokens and then auto-regressively just producing more is called decode.
Okay. Cool.
LLMs these days, a lot of the GPTs are called decode-only models, right? So this is the decode phase. Basically,
what's a decode-only model?
Yeah, so basically the way that things used to work is that there used to be two separate parts of the model for doing encoding of the past input and production of new output. Right.
Interesting.
And now we've moved up to this decoder-only model, where you're actually using the decoder plus, as I said, the KV you've generated for previous values in order to produce future values.
Interesting.
Yeah.
Yeah.
Decoder-only LLMs. So when you split it apart, you basically split it on the generation of KV based on the input, based on your prompts, based on your queries, everything like that. You split that apart, the prefill generates the KV, and then it starts sending the KV to the decode machine that it will be used on. And it does it smartly because it doesn't wait until you have it fully done all the way to the end. You can actually send, because LLMs produce KV layer-wise, right? You're doing layer by layer by layer by layer. You send the layers earlier, you start copying them over, so that the cost of transferring it is overlapped with the cost of computing it, right?
I see.
This is commonly referred to as compute communication overlapping. It's a thing that DeepSeek actually did for training as well. Go read the DeepSeek v3 paper if you haven't. In sending it to the decode machine now has basically its context of the past, right? To use an analogy here, you've done your research for your homework, right? You've done your research for your research paper. It's now time to start writing. And then the decode uses that KV to begin generating tokens.
Yeah. So how does the decoder know to start generating tokens if it might not have had the full KV cache? I didn't know the KV cache was layered, but that makes a total sense.
Yeah. So it's actually blocking, right? So you do an asynchronous send, but you have a block, basically a blocking
I see.
receive.
Like don't generate until
don't generate until you have the KV cache.
And that's because you always know how many layers there are in the KV cache before it sends over.
Yeah, so the number of layers is basically the same as the number of layers in the model.
Okay.
Right. So the model has layers, and the KV cache is like intermediate or it's like on each layer.
I see.
Yeah.
Okay.
Does the disaggregation only make sense if you are going to pair it with some of the other optimizations in Dynamo, or is that something that in and of itself could
standalone? It can produce enormous benefit. It's probably, it's crazy to say that just using a software technique, just splitting it apart on the same number of GPUs, just splitting apart these two things on Llama 70B, for example, yields over a 2 times increase in the total number of tokens that are generated per second across all users at the same per user TPS, right? Because that's what matters.
Yeah.
You have to keep the same latency, but how much throughput can you increase?
So as let's say, so in that case where you split so that some decoding's happening on half the GPUs, let's say, as the decoder is generating tokens, is a KV cache already starting to prefill? With some of the output?
So they're basically you're once the prefill machine gives up, quote unquote, gives up the prefill, once it transfers it, it just basically removes it. It says hey, I need KV space is basically the ability to do work for prefill machines. It's do I have enough KV space to do this thing? So it lets it fly to the wind. It lets it be evicted because it's no longer being used to generate KV.
Yeah.
And then it can accept new requests that'll use that memory.
Does this fluctuate, or do you have to specify how many GPUs you're using for?
Yeah,
each stage?
that's a fun one. So for static applications, let's say you're always feeding in 3,000 tokens in and 2,000 tokens out. It ideally wouldn't fluctuate. If you have set it up right, you'd basically be doing a batch thing where you would always send the same amount and it would be perfectly planned. But life doesn't really work like that. Users send hundreds of thousands of tokens 1 second, and then
every one of my ChatGPT threads is wildly different.
Yes, exactly. Right. So every single call is massively different, and in aggregate, amongst a bunch of different users, it's also highly varied per over time. Right. A good example of this is people submit batch work overnight because they have better latency guarantees, and it actually in some case for some service providers it's cheaper, right? So suddenly nighttime comes around, people start submitting batch jobs, and they're probably completely different than chatbot applications, right?
Yeah.
So in real time, the need for how many prefill GPUs you need and the need for how many decode GPUs you need is completely non-static. It changes moment to moment. And that's actually some of the stuff we're working in Dynamo, basically allowing decode machines to either become prefill machines, which is a future thing we're working on, as well as allowing an overarching orchestrator to say, hey, I probably need more prefill machines, so maybe I should mutate some of the decode machines into them because they have the same weights, right? You can actually tell it, hey, you're a prefill machine now.
If it became a prefill machine, did it then need to go and it needs to get the KV cache from a different GPU?
No, it'll start receiving new requests, so it'll fill up with KV for those requests, and we'll send them along. Basically, it's a pipeline, right? The prefill receives the request, it generates KV, it pushes the KV, and then it accepts new requests, and then once decode receives the KV, then it begins generating tokens for that query.
Now, one of the cool things that I've seen from Dynamo is that you said that you throw the KV cache to the wind, but that's not exactly true.
Yeah, that's not actually true. I was for prefill machines, depending on how you've configured them, that may be true. But oftentimes KV is valuable, and KV may be reused between queries. So a good example of this is multi-turn chat, right? You're chatting with ChatGPT, you have this context that's basically stayed the same throughout the entire conversation, and you've added on little bits of it, and the context has grown, right? If you threw away the KV cache for the conversation, you'd have to like recompute it every time you keep talking to the chatbot, right? So you really don't want to throw it away, and simultaneously you want to ensure that future queries that are aligned with that KV, that use that KV, whether that be because it's multi-turn chat or because you're using an agent that has like a similar corpus, you would really, really, really like to keep it somewhere. So we have two things in Dynamo that like really, really are very useful for doing this. One is a global KV manager that allows the offloading of that KV cache, like when it would be evicted, onto mediums that are not the GPU memory, where they're, that's actively taking up space, onto stuff like the host memory, which is like the RAM on the machines, and then onto disks or SSDs, NVMe drives. Basically, you have this hierarchy of cache where the HBM, which is the GPU's really, really, really fast memory, that's quite, quote unquote expensive because it's used for
high value.
Yeah, high value. And then you've lower tiers like host memory, and then it's like incredibly cheap to store stuff in cold storage on disks or NVMe or other storage modalities, as long as you can get it back into the system when it's necessary. So basically, this KV cache like offloading allows you to like store leftover KV in the fridge for later, and then like when someone's hungry, it fetches it.
Yeah. How much like faster is it to store this in cold storage versus recompute it?
So
I guess that wildly varies based off of how much.
Yeah. So it kind of depends. There's this interesting trait, which is that prefill, as it stands right now with current forms of attention, is usually quadratic with respect to the number of tokens generated, because you have to do attention between all the tokens in the sequence. Mm-hmm. And that means that as your ISL, as your input sequence length gets very, very long, you're scaling up. The curve is quadratic. The cost of storing it is different, because the amount of KV that you store with respect to the number of tokens is actually linear, and the cost to retrieve it is also linear. So as the sequence gets longer and longer and longer and longer,
it becomes more advantageous.
It becomes even more advantageous to move stuff to storage. Yeah.
What's like a sequence length where this really starts to pay off?
It completely depends on the model, and completely depends on what GPUs you're running it on. It could be as low as like 1,000, 2,000 tokens, but you really start to see enormous benefit once you get into the tens, hundreds of thousands of tokens. There's one more thing though, which is that even if the cost of retrieving it from storage, even if the time cost is high, you're actually you're avoiding the need to do prefill work, right? Because you're still retrieving it, even if it's a little bit slower, right? You end up with a situation in which the amount of GPUs that you need to do prefill is actually lower, because that request is not hitting prefill nodes anymore.
Yeah, makes sense. What's like an example of a real world application where the input sequence length becomes very long, very early? Well, I mean, I guess anything code gen.
Yeah, code bases are enormous. Code's kind of a freebie though. Really long conversations, places in which you're doing other forms of retrieval, like like applications like deep research or Perplexity, where you are basically taking a bunch of stuff that's retrieved and using it for a given context. That generates a really large context at the start, because you're basically doing retrieval from the internet or another corpus. And that really generates a lot of initial context very, very early.
Yeah. I don't know if this makes any sense, but would it make sense to put like essentially like pre-fill a repo and then put that in cold storage if you know that repo is going to be accessed a lot?
Yeah. Okay. Yeah, that's super useful.
Okay.
Right. Like if you have a bunch of agents that are working on a code base, which is a great example of this, and you are just going to like retrieve it or retrieve chunks of the code base contiguously, you'd want them to be in cold storage. And you'd want them to be like readily accessible. If you were, for example, to like launch a bunch of agents that are going to like work overnight on a new feature, right? You'd want to be like, okay, I'm going to pull that from cold storage. I'm not going to compute that.
Okay.
And just on that same note, would it make sense to almost have like async of basically calculating the KV cache, not at time of query?
Yep.
because you know it's going to be, if it's an agentic workflow where the system prompt is always the same.
Oh my God, disaggregated inference.
You should keep it right there. Exactly. Yeah. The other technique there is, if you know that something's going to be necessary, you should just prefetch it from cold storage, right? That's another thing that Dynamo enables, right? Which is that you can add in your control flow, like if you know it's going to be useful this long or is going to be needed after this long, you should immediately evict, move to colder storage, and then move to hot storage right before you're going to need it.
Oh, interesting.
And that's one of the things that we aim to enable with Dynamo going forward.
Is that live now, or is that coming?
So for certain frameworks, actually I should clarify. For the common LM serving frameworks, there are 3 that we currently have support for: SGLang, VLM, and our own NVIDIA's inference serving framework called TensorTLM. We call these like runtimes, which are basically like how you generate the actual tokens, right? TensorTLM has support that we added for basically telling the KV cache, like eviction policy that is used to evict things from the KV cache, or like decides what to evict or to remove from HBM. It gives you the ability to give it additional information, like I'm going to need this in 20 seconds, or I want you to keep this for 10 seconds, and if it isn't useful, then it falls off. It's a priority-based KV eviction is what we call it. So there's support there immediately, like right now for that. But we want to get more advanced and start sensing these things and detecting like when we can do this form of optimization automatically.
Yeah, that's super interesting. How would you go about sensing what you would want to, I guess?
Yeah. So one of the easiest ways is not really even sensing. It's the user just telling us, right? If you're running like a common agent framework like LangChain or Llama Index, or basically any framework that like has like prior knowledge of like the loop that it's going to run, right? You could just provide that information, right? You could say like, hey, here's the tree of all the things I could do. Here's how long it's going to take. In the long term, and I haven't thought about this much, so I'm gonna go on a limb and maybe muse about the future. In the long term, it might make more sense, or a lot of sense, to just sort of gather statistics in aggregate. Like notice, hey, this person's running this agent a lot, right? It's like generating this, or it's retrieving this context very constantly. It's also like tacking on extra context of about this size, and then it's going dormant for a little bit to call a tool or something, and then coming back in a bit. You can generally basically like trace workflows that like use KV, because the KV, one of the ways that Dynamo works is it actually tracks where in the runtime when KV is evicted or when KV is added. Because of that, you can extend that tracking to, hey, I'm like doing something inefficient here. At this timestamp, I generated the KV, and then I evicted it, and then I generated it again, and then I evicted it again, right? Like if you have that pattern, so that indicates that you could probably do something better. Yeah.
So all of this, I mean, super, super cool, and obviously drives a lot of efficiencies. But the one that makes the least sense to me, but also arguably the most cool, is the essentially intelligent routing to machines that have the KV cache that you are going to use.
Yeah.
How does it know which machine has the KV cache that's relevant to your query?
Yeah, so I that's a great question, because we literally just talked about it, and I kind of alluded to it too, which is that Dynamo, when integrated with a runtime, generates these events, right? These events basically tell you, at this timestamp, the KV has been evicted, or the KV has been added to a specific machine or a specific instance, let's say, because we have multi-node models. It says, hey, this specific instance just added this KV, or this specific instance just added or just removed this KV. And we actually have this component that we call a router, right, that tracks that. It takes in millions of events, of these KV events from thousands of instances, and basically says, hey, here is a sort of time-shifted view of what the tree of all the KV looks like. Here's where everything's stored. And when you are choosing where to put a request on which decode node or which prefill node or which combination of the two to put stuff on, you can actually look at that tree and say, hey, I can minimize my work because 70% of it's already done on this decode node right now, right? You only need to compute that last little bit of context. And you can also use the router to identify places in which you need to move KV, where if something's way too loaded or way too hot, right, you may need to like branch the tree a little bit and say, hey, this node which has this KV should also probably be on this other node right now, because if it were, then we would be able to like offload and do load balancing, right? So the router is responsible for that and is capable of both simultaneously maximizing for the chance that you have to do less prefill work. You have more of a prefix match, or like a context match on the KV that you've already generated, or it may also choose to like not route to that because that is like super overloaded, and may route a request to someplace where it may need to be regenerated, right? Or you might move it through other forms of transfer, but it may need to be regenerated. But once it's regenerated, that new instance is capable of handling requests that would have normally gone to this one overloaded instance. So the routers both do simultaneous KV-based routing, which is like prefix maximizing, and sort of like load minimizing, like avoiding overloading given instances.
Interesting. Where does the routing taking place? Like, is that
it's in, so like when you do a deployment, right? Mm-hmm. They're physical machines on which you're running. The router lives in that data center because you want to minimize the round trips of information. Like if you added extra latency, that's no good.
Yeah.
Right? So you have it running on some CPU machine or other machine or even on GPUs in the same place that the other that the actual prefill and decode workers are.
Yeah. Super interesting. So you said for Dynamo there were three things. We did the disaggregated inference, routing.
KV cache management, which is the ability to offload to the hierarchy.
Oh, right? I see, to like the cold storage.
Yeah, exactly.
Okay, interesting.
Yeah. So we have like this cohesive set of things that really like attempts to make when you are disaggregated. Sorry, to be clear, all the KV-based stuff like the offloading and the routing helps the aggregated scenario as well. You don't have to use disaggregation to get benefit out of Dynamo. So
interesting. Like if you just use offsetting or offloading the KV cache and routing,
because aggregated workers are still computing KV cache, right? They're still generating KV tokens.
Interesting.
But they're just doing it in a way that like contrasts with the decode work that's going on. It's sort of like jockeying for the same set of resources.
Yeah.
So I have a question because when I think about who's a prime consumer of something like NVIDIA Dynamo, it is somebody who essentially is serving these models, and that might be used by an end customer. And obviously, end customers might use the models in a variety of different ways.
Absolutely. Yeah.
And so when I think of like the KV cache, in my head, I don't know how unique a KV cache is. Is every user going to have their own KV cache, or is it actually, a million users that are going to be roughly using the same one?
Yeah, that's a great question. I think that like if you look at like retrieval based stuff, you may see like a lot of overlaps, but like one of the most gimme overlaps is the system prompt, right? If you have something with the same system prompt, everybody's going to have like something that was like 100% necessary. But that's like a little bit too easy. Like even amongst users, right, you may have like a common set of information that's retrieved, or in the agentic use case, you may have a context for your company, right? Let's say you have a bunch of agents that are running different functions within your business, right? Those agents may all have like some set of shared context that you want to put first, by the way, because then you have a prefix match. And then, once like there may be added context that's specific to that agent, but you still have a prefix match on this thing. You can think of it kind of like a tree, right? Like, the context branches here, but there may be like sub branches that are still shared, and then you eventually get to the leaves that are just like completely unique, which are
and that could even be like users. Different like threads within my application for different like use cases. Absolutely, that I as a user have each a unique KV cache.
Yeah. Or like a KV cache that's like somewhat shared, but like branches off into like different things that are specific to each of the threads.
That's one thing that I guess I didn't intuitively know before this, is the idea that like, the KV cache, because obviously it decoding is essentially adding to it as well, that it's almost like you can pick a small one that's like 50% of a task that everyone might start from, like the same starting point, and then it branches off. I thought that a KV cache was almost like it just exists. It's one KV cache for one task, but the fact that you can sort of build on top of it and create different flavors, I think is super cool.
Yeah. Like this is on a really like hard tangent. Like for code applications, like if you're building a code application, it's actually really important to ensure that like your code is returned in like an order that doesn't thrash the cache, right? Like if your code is
thrash the cache.
If your code is returned in a different order, included in the context in a different order, then you don't get a cache hit, because it's prefix based, right? It looks from the beginning and then it chooses as much as it can from the beginning, because KV is positional. So if you have like, let's say you have two sentences that get retrieved, like sentence A and then sentence B is not a cache hit for sentence B, sentence A, right? Because even though it contains the same content, the order matters because you're looking from the prefix to the end, and because attention is directional.
Interesting.
Yeah.
And so, I'm thinking about, you mentioned commonly asked or commonly retrieved information.
Yeah.
I mean, I think of like, there's probably a ton of data on what types of, what are the most common questions that something like a ChatGPT gets.
Yeah.
In which case, that probably is going to get hit even across many, many different users, because people just use that application in a very similar way.
Yeah. I think like initially, before like I looked at the statistics, I was like, why are we storing this in a tree? Like, it doesn't make sense, right? Like if you were, the only reason you would store it in a tree is that you think that there will be overlaps and that there may be like splits off those overlaps, right?
Yeah.
And lo and behold, there's actually like a ton of overlap of like small of some pieces of some length, not the whole prefix, that like split off, whether it be the system prompt or context that's shared between two different users, two different agents, two different anything. And also, even just as you said, with regular chat queries, there are data sets out there that like you can like look over for that are like basically like representative KV cache hits, where like even amongst users, the things that their contexts have like a moderately large cache hit, which is crazy.
How hard is it for me as like an application owner, let's say, to leverage some of these KV cache optimizations?
It's actually not really hard at all, right? So in Dynamo, we have it integrated into TLM as a runtime. For VLM, we're working to upstream these events into VLM so that we can integrate with them. But we have a patch that you can just apply over VLM that hopefully should not have any conflicts anywhere near soon. It's actually put into place in VLM that isn't touched often. In that sense, right? Like if you are running inference already and you're using VLM or TLM to serve your models, right? You can move to like a Dynamo-based worker that wraps that runtime, and then also just add the router, and you instantly start getting benefit.
Something that I think, agentic style workflows and just the concept of agent has become super popular recently. And certainly, I think what a lot of people haven't really made the jump in their head is just how many more tokens that means need to be generated on Earth, right? Because we're no longer generating tokens for humans; we're generating them for computers.
Yeah, it's like completely isolated from humans. Like the output is not tokens; it's a task, right? Like it's like, okay, like did this embodied agent like correctly feed my dog, right? They don't care that it's like thinking about like, should I put the bowl here or should I put the bowl here? It's just like the outcome, right? And as you increasingly as you see more automation from agents coming out, right? Like they're just gonna be more tokens generated.
Yeah, there's no ceiling to that.
No, there really isn't. As I said, as you unlock more applications, right? Like suddenly, if you have something that is like immensely valuable to humanity, right? The cost at which you're willing to let it reason forever is basically like negligible, right? Like if you had something that was able to design a new, more efficient like car body design. Let's use something way out in left field, right? Then that's like 50% more fuel efficient. Suddenly it's like, wow, I should just let this thing forever, right? If you can if you have machines that are capable of doing thinking, right, and the thinking produces better and better results the longer it thinks, right? Eventually, there's potentially an end state, although maybe we're not fully there yet, where for like very important tasks that like produce a lot of value, you can just put a bunch of machines in parallel because, right, you can actually just scale out machines, right? Humans are actually harder to scale out, especially for those that are like very, very, very talented or very, very like deep in their fields, right? And you can imagine a situation in which like the PhD researcher, like I know that's like really a big topic right now. The PhD researcher works with these agents that like run their experiments for them, right? The researcher becomes like the person that designs the hypothesis, and then the agent executes upon that hypothesis. Or, if you have some very, very, very smart agent, maybe it designs its own hypothesis and works with the humans to like refine it, right?
That's what I mean. I just think we're in such a cool time, and you are effectively making the step forward in, you kind of alluded to it earlier, but like driving the cost of intelligence down.
Yeah.
And when the cost of intelligence goes down, I really liked I was visually thinking of like a 3-dimensional space.
Yeah.
And there are all these dots of like things that we could do.
Yeah,
if we
totally.
could just push one or more of the axes further out.
Yeah, exactly. Yeah, so that's actually that's how I think about it too, right? Like applications are basically like points in space. Like there's one right here, there's one right here, there's one right here, and if we raise the level of intelligence, that's great. It moves up here, right? But there's also other axes like, hey, we move the cost gets better, and therefore like we move this out, right? What's crazy, and one thing I love about Dynamo that we've provided and are also like dedicated to working on in the future is basically these techniques like disaggregation and other techniques like speculation, which I mentioned, that allow you to like tweak the domain, right? Like reasoning, right? You may have just generated a lot of tokens, but you may also do something like consensus at n, where you generate a bunch of different strings and then like choose the most common one, right? So in that case, if you're making something cost less, right? You can also use that cost savings that you have to make the model smarter, right? So like making tokens cost less is, with these techniques and with the toolbox that we have available to us, basically also the same as like making it smarter at the same cost or making it faster at the same cost.
Yeah.
Which is crazy, right? It's just like if we can drive the cost of tokens down and down and down and down, right? More and more is just going to be done with AI.
Applications unlocked.
Yeah, like it just unlocks more and more and more and more.
I have a question on the latency.
Yeah.
There's like time to first token and inter token latency.
Correct, yeah.
And like loading, essentially like loading KV cache that's been pre-calculated.
Yeah.
Seems like something that benefits time to first token.
Yeah. So again, as I said, it kind of depends on like the length, right? Because it's kind of like two graphs where like one is linear and the other is like quadratic, where like the quadratic line and the linear line meet at some point.
Yeah, I see.
So there's like some tipping point at which like it makes total sense to just always do retrieval if the retrieval is an option of that KV. Yeah.
Yeah, I see. How much of Dynamo, like what optimizations in Dynamo impact time to first token versus inter token latency?
Yeah. So as I sort of said, like disaggregation is a technique that disaggregates prefill and decode, and like prefill and decode are very funny because like that literally splits out time to first token and like one machine is really responsible for the intertoken latency and one is responsible for the TTFT, which actually is like one of the biggest benefits of disaggregation we have not talked at all yet about, which is context or prefill and decode want different configurations. So like for some models, like, context, I can't speak generally about all models because every model is different. They may use different form of attention. They may use mixture of experts or something. But let's just talk about like DeepSeek R1, which Jensen talked about in the keynote. Jensen on the graph pointed out like different points in the curve and how they differ, right? And the key thing there is that like one of the reasons that like the aggregated line looks like this and the disaggregated line looks like that is that as you push higher and higher latencies, lower and lower latencies as you get better and better, because the TPS is the x-axis, so more TPS means lower latency. As you push user TPS, Decode actually wants, on DeepSeek specifically, wants a lot more GPUs in the decode phase. Like it wants to do high amounts of expert parallelism. It wants like a lot of GPUs doing things in parallel, because it means that you can do like very high batch size but still very, very fast calculation of new tokens. So that's why like on the DeepSeek curve, there's like basically like there's like a cliff for aggregated, and then disaggregated stays like high for a really, really long time, which is just that like you can still keep using, you can use these like really, 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 really massively parallel configurations of the decode instance. But the problem with aggregate is it also has to do context, and context does not scale in the same way, right? Context for DeepSeek R1 likes to have smaller numbers of GPUs in the context phase, prefill phase. And because of that, that means that like in the aggregated sense, like you're getting kind of the, it's weird to put it this way, but like the worst of both worlds, right?
Yeah.
Like neither your context nor neither your prefill nor your decode are getting the configuration they want, because you have to like kind of find something in between.
Is that why it performed so well for R1?
Yeah. R1 specifically has like a bunch of things that DeepSeek themselves actually designed into the model that makes it really, really, really disaggregation friendly.
And what was the performance gain for disaggregation?
The performance gain for disaggregation was at around 300 tokens per second per user. You can generate 30 times more tokens.
That's crazy.
per normalized per GPU.
Yeah.
Yeah. It's wild, right? Like you have these. To be very clear, those are projected numbers, right? So we're like that's like the upper bound of like what you can do with software. Like that is absolutely amazing. But yeah, I mean, disaggregation really allows you to have these two different configs. It allows you also to like have a different load match between context and decode, or prefill and decode workers, right? Which basically means like, hey, I have like a bunch of really long ISL, right? I'm gonna want more prefill workers. I can scale them up individually, and I don't have to scale up decode. But if you're in an aggregated scenario, if you get more prefill load, you just need to scale up more workers. You don't have the ability to granularly control what the load match between the prefill phase and the decode phase is.
This is crazy. It seems like NVIDIA Dynamo, I guess zooming out, like inference has so many different levers.
Yeah.
There's different types of, and that makes sense because there's an infinite number of space of applications you'd build,
Yeah.
of ways that you'd leverage context, of what you'd want to put in the context of, how much you're using a particular model for a continued task.
Yeah.
And with agents, that space just proliferates even more.
Yeah.
And given all those different levers, I haven't heard of anything like NVIDIA Dynamo come out that can really like optimize.
Well, I was just gonna say, and the coolest part is they made it open source.
Oh yeah, it's open source.
Yeah.
Oh, we didn't even mention that. Yeah, it's all open source. There are a couple of things that we haven't mentioned. We can just rattle them off, and we can dive into them if we find them interesting. We're also implementing and releasing a communication library that's used for the transfer of KV called Nixel. Yeah, so
that's cool.
it's going out open source.
Spell Nixel.
Nixl.
Okay.
Yes. So Nixel's going out. It's all open source. The router's open source. The roadmap is in plain view. Like we want to enable as many people as possible with this.
Yeah.
We want to enable as many runtimes. We want to enable like whatever people want to do inference with. We want to enable.
Yeah.
However people want to do inference, like if they want to do multimodal models, that's something that we're like actively working on right now.
That's awesome.
Actively thinking about. If we want to do other forms of inference that may prefer disaggregation, we also want to work on those.
How do I get started with this? So it's open source. I can go to the repo.
Yeah. So you can go to the repo right now. We have a series of examples that will show you how to do disaggregation. We want this to be open as accessible as possible. So we actually have backends in Dynamo that work on your laptop. So like if you have like a Mac laptop, you can just run Dynamo, even though you can't do disaggregation because it's one one like chip, you're still able to like experiment and run with it, and then like you can move it off of your system onto bigger and bigger systems in very easy ways.
And so if I just need like 2 GPUs minimum, like on a on a single node.
Yeah, to start with just disaggregation, you could start with 2 GPUs. But as I said, right, the one of the things, the 2 of the biggest impacts that disaggregation has. So there are 3 total benefits, and let's go over them again. One is just scheduling gets better, right? Because you only have to schedule prefill and decode, and you don't have to like consider like, hey, should I handle this decode to get it off my plate, or should I do this other prefill that's come in? So that's one thing. The second thing is you can do different configs, right? So if you have only 2 GPUs, you may not even see benefit from disaggregation because you may not be running the configs that would yield that benefit. By configuration, I mean like how many GPUs and in what parallel strategy you're using those GPUs in order to produce output or in the decode or prefill phases. And then the third thing is that for the prefill and decode workers, you can do a load match, right? So if you have 2 GPUs and one's prefill, one decode, you have an arbitrary load match is 1-to-1, right?
Yeah,
so the more GPUs, the better. In our Jensen's words, the more you buy, the more you save, right? Like it gets better, you get better and better load matching.
You're better fitting to the problem.
Yeah.
But I mean, I think that's what this is used for, right? This is a lot like a scale problem, which is like the laws of scale. Like when you're talking about billions of tokens for billions of users, then that's where you really see the 30x then really matters.
Yeah, exactly, right? If you're talking about like industrial applications or like enterprise applications or applications that serve a lot of users, you want your tokens to be as efficient as possible, right? Because you can enable, as we said, we keep going back to this, cost basically means you can enable more applications. If you decrease the cost, you're basically just making more applications able to use AI, right? More applications able to use the power of these LLMs. And you should really be thinking about like starting using some of these techniques if cost is something that's sensitive to you. Now, if you're a researcher, right, and you really you're like working on 8 GPUs and you want it to be as fast as possible for one stream, aggregated may still make sense. But you can still use KV routing and other techniques that I use in Dynamo, right? And
it's baked into the runtimes. So
yeah, it's baked into the runtimes, yeah.
That's awesome. So Dynamo's released. It's open source.
Yeah.
We can check it at the GitHub or from the GitHub.
Yeah.
Are we hosting it? Do we have any examples? What's like the easiest way for someone to try this out or experience the benefits?
We have multiple examples on the GitHub repo. You can pull those up on your own machine. There are Brev boxes from NVIDIA that like you can run workloads on. You can pull those examples into a Brev box and start working with them. There are also a number of tutorials. So if you're here on the GTC floor right now, I say that actually as I'm sitting right post announcement in our headquarters. But if you're on the GTC floor later today, you can go to our both our tutorial session or our Connect with Experts that happens later in the day. I actually don't know the times off the top of my head. We'll have a banner on that, hopefully. And you can come and chat with us. I'll be there. If you see, I think me or
I think both of us will be down there.
Yeah, if you see us on the GTC floor, please come talk to us. I think I'm very happy to answer questions. But if you're looking to get started and you're online and you don't have a GTC ticket, you won't be there. Don't worry. We have a series of video demos for how to get started with Dynamo, as well as examples that will walk you through exactly how it works, exactly what the levers we provide are, and generally provide you, hopefully, with a good, box opening experience.
Amazing. Yeah, dude, amazing work for you and everyone on your team putting this together. I think, this is super exciting, and 2025 is the year of agents, the year of all these proliferating new use cases.
The year of tokens, token factories.
I mean, that's what I just think it's so cool to, be part of this company and see how we're pushing the limits, obviously, in terms of the chips themselves and the speed and even how much memory they have and all of that, but then all the way through to inference and pushing the limits of inference. And, you are effectively, driving, putting intelligence again, because it's not hyperbole to say that it's making intelligence more accessible to everybody. That is what this is.
More accessible, more cheaper in general. Like accessibility and cheapness are sort of related, but there's also just like for large scale applications, it's just cheaper, and more efficient. And as you said, right, like it's pushing down the cost of intelligence, which basically allows you to do a bunch of the different things with these levers that we've talked about. So it's really exciting to me, and I just see like so much promise in the ability to like make generation cheaper.
100%.
Right? Like that's more code generated. That's more scientific discoveries accelerated. That's more cool applications, or like I would love to see eventually like a video game that is like LLM powered. And the more we push on this frontier, the closer we get to those types of applications. The crazy, wild, emergent behavior and new applications that you wouldn't have ever seen if not for cheap tokens.
Yeah, absolutely. Well,
yeah.
Awesome. Yeah, thank you.
Thank you.
Yeah, thank you.
Check out NVIDIA Dynamo.
Yeah, we'll put links here.